Hello. In today's class, we are going to cover the concepts that we are going to focus on for the exam 3. And this exam is going to primarily cover the concepts of fault analysis, including symmetrical faults and how to calculate them. So the first major topic that we're going to cover is the concept of where does the energy for faults come from? And this is evolving a little bit because of inverter-based generation that you typically see with PV systems, distributed generation PV type systems. So those will vary quite a bit, but those tend to be kind of a small proportion of the total fault current that is available on a system. So we really are going to focus on larger scale systems. And for most of the case, that fault energy is coming from synchronous machines, particularly synchronous generators. You do have some applications with some large synchronous motors. In the case of some synchronous condensers, you actually have some fault current capability. But the way that you analyze a system with a synchronous motor or a synchronous generator is essentially the same. So we won't identify those anything different. But essentially, when we do that, we're going to have to figure out where that power comes from. And so we have to do that from the concept of modeling a synchronous machine behind some sort of time-varying reactance. And the reason why there's a time-varying reactance is because the energy supply is going to vary out of the machine. And so what we try to do is we try to simplify the energy out of the machine and we break it down into three distinct energy periods, if you will. There's the subtransient, which is the quickest and usually is gone in 3 to 5 milliseconds. Then we go to the transient value, which is from 3 to 5 seconds all the way up to 30 to 60 seconds. And then beyond that, if the fault persists and it hasn't been disconnected from the system, then you go into the steady state condition, which is greater than 30 to 60 hertz or 30 to 60 seconds and cycles, I'm sorry. And then that can last for however long your machine can operate before it burns up. Because under fault conditions, you're putting out way more current than what the machine is rated for. So you can't do that indefinitely. But from a faults perspective, and we need to analyze the system, we're going to assume that our generators are in fact going to be able to feed that fault for a very long period of time. So our power source exists in our synchronous machine model, and our power source is just a voltage source in series with the internal reactances and resistances of the synchronous machine. And so we usually try to simplify that and ignore the resistor that we have associated with there and really focus on just a single resistor, our synchronous reactance term there. And then that's the term that is going to vary whether it's subtransient, transient, or steady state time. So then our output current becomes just a combination of those different energy level times, if you will. And then how do we take care of it? We have an exponential decay because these are inductive circuits. The exponential decay is going to result in transitioning from one time period to another. So you can see that each successive time period, we're dividing by a different quantity. We start out with the shortest time period, which is XD double prime. And you can see that in the shortest time period, all elements are going to contribute, the XD double prime and the XD prime. And then when that's the shortest time period, we also see that in the time, the TD prime value, both of those are there. So you can see that there's a canceling of not only the XD and the XD, but the XD prime as well. So both of those terms are going to be in there. But if you're trying to solve for the equivalent or effective AC component as a result of the fault, you would apply this particular equation here. If you want to see a DC component, because the DC component exists primarily for the inductor storing magnetic energy. And so as it stores its magnetic energy, if a fault were to occur, that inductor current cannot change instantaneously. So it's going to start to discharge its energy to try to maintain that current value. But the AC component is still happening. There's a rotating machine in there. So that's going to kind of ride over that DC value. And so if you look at the three curves here, those are for each of the phases. So we have phase A, phase B, and phase C, the three different phases. And when the fault occurs, the fault current is the same before or after, but the inductor now may be discharging its energy level to try to keep that current that constant current. And so you can see how you get a DC offset that eventually decays away for both phase B and phase C here. Phase A doesn't have any because it was closed when there was no, the fault occurred when there was no current there. So there's no instantaneous change in those values. And that's why we need to examine systems with their DC component, making the faults no longer symmetric about the x-axis. Because if you have a three-phase fault, which is the most common, I shouldn't say the most common, is one of the more common faults, then what you're going to end up having is the case where you're going to have some DC offset in one of the phases. So now we understand where the fault energy is. Now what we want to do is, if we want to find a fault current or a peak fault current for any of those time intervals, we would like to automate the process or simplify the process so that we can calculate fault currents for any bus on the system at any particular time frame. And so what we want to do is if a fault occurs at a particular bus, we can figure out what that fault current is going to be just by calculating what the voltage is at the fault, the pre-fault voltage. And then we would go ahead and examine what happens because of the fact that we actually introduce a fault. And so that the way that we do that is we have a bus here, and we're going to put in a fictitious voltage source, which that is the pre-fault voltage. So if we were to have a fault at this location, our voltage is not going to be V pre-fault, it's going to be 0. So we inject another source that has exactly the same magnitude and angle as the pre-fault voltage, but it's just in the opposite direction. And so what ends up happening is that becomes 0 volt, which is the condition for the faults. And so by adding that with superposition, we can simply just go ahead and have our one case where we analyze the entire system under pre-fault conditions and get all the bus voltages because that's our system. We've done superposition where we've had the entire system done. Now we need to add our single or additional voltage source in there. And then that's going to force us to go ahead and see how the system has changed. And then we just add it into the system or the pre-fault values, and we actually get what our final voltages are going to be. So if imagining that there's a fault on bus 2, our change in V2 is going to be our superposition voltage source there, which is just negative the pre-fault voltage that we have there. The other change systems, the other voltages are a result of using our Ohm's law approach. And so what we end up having is we have a ratio here. So we have our fault current flowing, which is VF divided by Z22 at bus 2. But the actual impact on voltage at the other buses can be found by modifying or monkeying with the Z12. Now, this is the Z values here you're going to get from inverting Y bus to get our term Z. So by simply adding that superposition voltage there, we get really simple, easy adjustments. And now we can go ahead and get all the changes in voltages. So after the fault occurs, our new voltage at bus 1, for example, will be its pre-fault voltage plus the change in voltage as a result of the current flow there. Once we have the change in voltage, now we can actually calculate what the fault currents are going to be to the fault because we have a system. Let's say this is V1 and this is V2. This has some sort of impedance. And these are post-fault voltages. So to calculate this current I, which feeds the fault over there, we just go V1 minus V2 divided by Z of the actual line. So this really greatly simplifies our approach to calculating fault currents because now all we have to do is apply Ohm's law once we have the changes in voltages. Very, very quick and efficient way to do that. And it can be automated. You can set it up to run through all the different buses and you can look for different characteristics like where's the worst case fault at bus 2 or bus 7 or whatever value you have. So it really makes it quite a bit easier to go ahead and calculate that. Here is exactly what we said. If you want to calculate the post fault current value on a line, you take the line difference between the two, and you can either divide that by the impedance of the actual line. So that's not Z bus, that's the actual impedance of the line, or you can multiply the admittance over there. And you'll notice I have minus Yj here. that is minus Y bus of IJ. And the reason why the minus sign here is because remember when we build our Y bus, we solve for the diagonals by summing them together, and then we take the negative of the actual admittance between bus I and bus J. So that's why we have the negative term there. So it's very important if you're going to use the terms from Y bus, it's perfectly fine to do that. Just make sure you take the negative of that value. Then we moved on to probably the most important part of this sort of areas of topics when we do fault analysis is to do positive, negative, and zero sequence network analysis for faulted systems. And symmetrical components is only applicable or only available to a system that's perfectly balanced except for the one point where the fault occurs. And what we need to do is we need to couple those systems together so that we can connect those networks and we actually can get current flow during the fault conditions. It does not work if you have an unbalanced system. And so one of the more difficult things moving forward is now we have unbalanced analysis, particularly when we put distribution systems, when we put PV or we put wind or whatever, and we distribute it. Now we have the possibility of having a lot of unbalance in our system. And so as a result, we actually have to do a different approach to solve for fault currents. We can't just do symmetrical components. You can still use the zero sequence, negative sequence, and positive sequence currents at a particular bus. So once you have all the phase currents, you can use IA, IB, and IC. You can use this approach and you can invert and solve for the symmetrical components, but you have to get those from the phase currents. You can't actually put the sequence networks together in such a manner to derive I0, I1, and I2. You have to get them from the phase currents, which is not a big deal. It's just that that's what the relays do all the time. They don't necessarily know what the system is. They're just actually calculating those values, but they still need to be done. They still need to be calculated. So we'll use symmetrical components because a lot of the relays are set that way. And we can see that we have a positive sequence network as shown or as indicated by the 1. So that would be the positive sequence. We have A, B, C rotation. All the magnitudes are exactly the same, and the angles are offset by 120 degrees. In the negative sequence condition, we have, again, a balanced set of phasors, but the difference now is that the rotation is no longer ABC, but in fact ACB. And so the reason why they call it negative sequence rotation is if you were to rotate the positive sequence in the opposite direction, you would end up with the same values. And so they talk about double frequency because if you have the positive sequence going at a positive 60 hertz and the negative sequence going at a negative 60 hertz, those look like a difference of 120 hertz because they're going in opposite directions. The zero sequence, I don't even show the network over here, but I don't need to because they are in fact all exactly the same magnitude and angle. And they can't be balanced because if we want to get ground fault current in a Y connection, it's impossible to use a balanced set of phasors because those will always sum to zero. Over here, the three of these added together will not sum to zero. So I talked a little bit about the A matrix. The A matrix or capital A matrix is just a way to go from my phase components to go from my symmetrical components to go to my phase components. And so this is all just in a nice tidy matrix because remember, I have IA0, IA1, and IA2. Those are the only three symmetrical components that I'm going to calculate because the B and the C phase ones are essentially very easy to calculate from the A phase one. So there's no reason to calculate B phase or C phase. We'll just use the A phase, which then requires us to build this capital A matrix. And the capital A matrix has this term A in here. Well, the reason why is if you remember, if this is IA1 and IB1, and this is IA2, and IB2 would be up over here, we can see that I have to phase shift IA1 by 120 degrees and have the same magnitude. So IB1 is simply going to be equal to IA1 phase shifted. So I'm going to multiply that by 1 at an angle of minus 120 or 1 at an angle of 240 degrees. And then to go from IA2 to IB2, I multiply now by 1 at an angle of positive 120. Well, if I develop this new term alpha and call it 1 at an angle of 120, then alpha squared is 1 at an angle of 240. If you remember, when you multiply complex numbers, you multiply the magnitudes and you add the angles. So we can very quickly go ahead and build this capital A matrix by using these alpha terms. But again, the capital A matrix only exists so that it makes it much, much easier for us to only need to calculate the phase A symmetrical components. So that's all well and good. We can go ahead and solve for the symmetrical components, but it doesn't really help us in our analysis unless we know what the phase currents are going to be. Well, that's the thing when we do it on paper, when we're trying to figure out what the fault currents are going to be in phase current land, we don't actually know what they are. So we can get those if we know what the symmetrical components are. So what we're doing with our fault analysis approach is to go from symmetrical components to phase components because we can calculate our symmetrical components. And so how do we calculate them? Well, we're going to go ahead and draw our sequence diagrams, positive, negative, and zero sequence, based on how or which way they go ahead and they interconnect. And drawing the sequence networks is particularly important for the zero sequence diagram because the zero sequence diagram has to have neutral connections to allow zero sequence current to flow. If we don't have zero sequence current flow, then we can't have any ground. So that's why it's so important when you're building your your zero sequence diagram, look at the neutrals and see if you can have zero sequence current flow. For transformers, it's even more difficult because I need to have a neutral connection and I also have to have the current flowing on the other side of the transformer. So one neutral connection may not be enough. In the case of a Y transformer, a Y-Y connected transformer, I have to have neutrals grounded on both sides to go ahead and to get that to operate correctly. If it's a Y delta, I only have the neutral on the one side, but because KCL allows it, I can actually get a circulating zero sequence current in the delta winding. So it works perfectly fine for me. So that's the key thing. You have to make sure that you understand how to set up the sequence diagrams for transformers and for generators and motors and see if they're grounded or not. The positive and the negative sequence diagrams generally are really easy because they look exactly like the system that you're analyzing. The neutrals don't make a difference. It can be connected, grounded or not. It does not matter to zero or to negative or positive sequence current because, again, they don't care. To note, the only one that has a positive, a power source is the positive sequence diagram. And again, whenever we actually have a fault at a particular location, that's where we're going to connect those positive, negative, and zero sequence diagrams as necessary to make sure that we have current flow. And until we couple those networks together, we have no power flowing in negative or zero sequence because there's no connection there. There's no reason for the current to flow because we're talking a perfectly balanced system. So that moves us on to topic number 8, which is how do we couple the networks together? Well, we're only going to consider 3 unbalanced faults. If it's a balanced fault, you will only use the positive sequence diagram and show the fault current for there. If you have a single line to ground fault, you must have ground fault current. So you have to have a zero sequence current. And how do you interconnect those systems? You have the positive, negative, and zero sequence diagrams all summed together. And this diagram does a really good job of showing you how the voltages are flowing, how the values are, and then my currents are going down in this direction here. So this is IA1, IA2, and IA0. I am strongly suggesting that to do your analysis, you make sure that you have these diagrams spelled out so you can actually see how you can get the current flow. So these are our references, and it's important to configure them this way. That's single line to ground. Next one is a line-to-line fault. So we take our positive and our negative sequence diagrams. Again, we're going to assume that current, our reference current, whoops, that's flowing in the opposite direction here. Do that again. So we have, oh no, it shows it right here. Okay, perfect. So we can see that we have our 2 currents here, IA1, an IA2, and then we have VA1 and VA2, which is of the voltages, and those voltages have to be the same as each other. So we get the voltages here, and then you can see that with the current flows, you're going to end up with opposite directions as shown, but that's okay. Again, this is just a reference. If things are in the opposite direction, it's no problem to go ahead and do that. So that's a line-to-line fault. Now we have the double line to ground fault. We have the possibility of zero sequence current flowing. So we're going to add those values there. This shows the three networks all connected in parallel. It does not show the 3ZN. If you have the 3ZN, you would include it right over here. But again, you take those networks and connect them that way. And then the last thing is, if you have a fault in a single line of ground fault, you're just going to use a superposition. So you're going to do it exactly the same way, but now you have to do it for each of the phase components, the symmetrical components, I should say. So you're going to have the negative, the positive, and the zero sequence. You're going to go ahead and calculate all those, and then you'll calculate the updated voltages, and then you can calculate the unbalanced current flow flowing to the fault. So here are the specific test questions. If you have a set of unbalanced phasors, I want you to not only find phase A, but also find phase B and phase C, which shouldn't be too hard because, again, in some cases, they're exactly the same. They're just going to be offset by that 120 degrees. So it shouldn't be too difficult to find A, B, and C from A. If I give you a three-phase load, you should be able to express that load in the positive, negative, and zero sequence networks. So again, that is based on, think about if it's a generator, think about if it's a transformer, if it's some type of load, where is it going to show up there, okay? So if I have a three-phase Y, a three-phase delta, can you get the zero sequence current flowing in there? You should be able to get the positive and the negative, but will the zero sequence current be able to flow? Item number C, which is draw sequence diagrams to make sure that you can accurately determine what the symmetrical components for a system need to be. So that'll be a very simple power system to go ahead and do that. Then we do superposition to calculate our fault current for a simple system. So being able to update the voltages, you should be able to build Y-bus for this. We keep going back to that, but again, that's a very important skill for us to be able to build those. So being consistent and going through and developing those diagrams. And then I'm going to go ahead and give you Z buses for three networks. So I'll give you positive, negative, and zero sequence network. I would like you to be able to calculate the phase sequence currents and voltages for an unbalanced fault. So calculating fault current and calculating what the voltages are expected to be, you should be able to do that. And once you have that, you can calculate the symmetrical components, and then you can solve for phase voltages and currents. And then the last one is if I've given you Z buses, then calculate current flowing through the lines for a fault on a bus. And so I'm trying to break these problems up in a very specific way so that if you have a hard time building Y bus, it doesn't necessarily mean you get no credit on the test, because you'd have to build Y bus in every problem. In some cases, I'll actually give you the output that you need for the Z bus so that you can actually go ahead and calculate it. So that's it for this exam review. I hope you have found this stuff useful and informative. And if you have any particular questions, feel free to reach out and I'll do the best I can to help you. Thank you very much and have a wonderful day. Take care.